Hi, this is Professor Snell. I am going to make a video about essentially about peak heat load loss, but it's in the context of designing or choosing an HVAC system and sizing it, including the ducts. Now, I'm just going to jam on this video. I don't know how long it's going to take. I'm going to cover a lot of stuff, so just scroll through it as usual. Um, In my section, I will go over this modeler that I'm going to show you in some detail in class. We'll just really try to deal with this. But I want to make a general comment. I keep saying this to people, but I'm not sure if you're getting it. So we're not mechanical engineers. That's not the goal here. We don't need to even be accurate in this class. What we're trying to do is understand the concepts. And generally, now I'm not saying you won't become a technical architect who actually designs HVAC systems. That's could happen definitely on smaller buildings, for example, or who knows what you're going to end up doing. But generally, what we're doing is just trying to start understanding the complexity of architectural projects and the simple point that we need to think about everything from the beginning so that we don't get trapped somewhere with a bad decision that was made without information. So we are thinking about HVAC from the beginning. We're thinking about climate because that's going to help. That's going to have a lot of effects on our form. It's also going to have effects on our HVAC. Then we're thinking about HVAC from the beginning because we need to have some idea of how much space we need for it. And we determine that by slowly learning about how the different systems work and by creating performance metrics that we are shooting for in our project. So the point is here, just relax. Let's try to get the basic concepts in, and uh, it's not don't freak out about it. Basically, is what I'm saying. This is where we're going, and I know this looks complicated. It's not. We're just really going to do one side of this, one zone. I mean, the zones repeat. Okay, so it's really not very much information. I'm going to start with a blank sheet, and we're going to go through it as a teaching tool. Another thing I want to say, I'm not a mechanical engineer. This is my attempt to make this simple for you guys. Um, or no, it's my attempt to make a teaching tool that helps us understand the concepts. So do not take this into a project and use it. There's way better ways of doing this. For example, a manual J calculation would be, and they're standardized, right? So you start making these little tools, it's dangerous. But for this class, I think this is good. So, and I'm trying to respond to the fact that I know people, maybe are still not understanding this heat load thing. So I want to start. This is a building that this is basically it comes with climate. Well, this is the team that developed Climate Studio at MIT is continuing to work on it, and so this is a building that they have is a sample building that they're using for different things. It's got a bunch of zones, and there's a cool plug-in to it that I want to show you as part of this video also, just to sort of make a point about where we're going and why you don't need to be in the end. It's good to do hand calculations now and understand how it works, but in the end, you're not going to be doing a lot of hand calculations. You're going to be using tools. And you're going to be friends with engineers. That's what I've said a bunch of times. Make friends with engineers. One of my best friends is a brilliant mechanical engineer, and he makes me seem really smart because I just ask him questions. And you want to partner up with engineers as quickly as you can on projects that require them. Anyway, okay, so this building. Let's talk first. So where are we going? We are going to, in the end, this is the peak heat loading for this building. Based on a bunch of assumptions. And what we're able to get to here then is a final cooling load, a heating load, so that we could size our equipment. And then we're able to size our ducts by figuring out the CFM required for heating and cooling, and then saying which is larger, and then designing the ducts based on that. And then there's a little worksheet here that we would use to do that. That's essentially all we're doing. But before we get here, and so you can scroll through this if you're not interested or if it's because this is kind of from last semester, but it's really important because before we get to peak heat load, we have to have building design, basically. Or we have to decide about a lot of things about the envelope and about shading, etc. Um, so last semester in my section, we did some work, and some people did a fair amount of work in the in Climate Studio in the thermal analysis simulation. And the way this works, so anyway, this is a three-story building. It's an office building um, with multiple zones. So if I'm going to turn off the architectural model and turn on the zones. So what do we have here? This is the layers for the thermal model. So I'm going to turn them all off and turn them on one at a time. We start with our zones. So this is a three-story building with 5 zones. So we've got 1, 2, 3, 4, and a central zone. This is an ASTM 90.1, an ASHRAE 90.1 standard configuration. And so it's fairly typical. We're seeing that the long sides on the north and south. Um, and we have 3/4 of these zones, okay? Then we have a slab where we're touching the ground. We have windows, and we have the floors. Okay, so the first thing, or the thing that we were doing, that we did last semester, or if you didn't, fine, I just want to talk about it briefly, is we did a thermal analysis of this design in order to optimize it for, and to go further, what we did last semester was we learned about all the passive strategies based on the climate and tried to optimize our form for those. And then we moved on to the envelope to make up any other, or to improve the efficiency of the design through the envelope design. And then we said, okay, next we would have to add HVAC, which is what we're doing this semester. All right, so if I go to, I've run a bunch of simulations. Let me go to the first one. Let's just look at what we have here. Oops, didn't want to pull that out. We have site EUI, that's energy use intensity. So that's the amount of energy that we're using on site per square foot. So it's kilobTUs per square foot per year. That allows us to compare apples to apples because larger buildings are naturally more energy efficient because they have less surface area per volume, and the surface area of the envelope is what you lose your heat through, or you gain your heat through. And so then there's a carbon calculation here. There's an energy cost. I'm not going to talk about those. Then there's a baseline EUI. So this is basically saying for a typical building, we're not going to even say where that baseline came from. It's just sort of an average building. This would be the EUI, so we're above it right now, and we haven't saved any energy based on the EUI. Then we have these charts down here, energy use intensity, which tells us the heating. So red is heating loads, blue is cooling loads, lighting, hot water, etc. And we can do that either EUI or per square foot, or total. And we can look at energy flows, which is very interesting because we have all these different categories down here that are split up between above the black line is gains and below the black line is losses. And together, this is just another way of expressing this information. Okay, so what we're starting with then, and what I'm calling the old school simulation, is a build. I just tried to make a crappy building. So I gave it a really bad envelope. It's leaky. No thought to, doesn't have LED lighting, etc. And so, because I wanted to get something above the baseline, so I accomplished that. We see that we've got a lot of heating load, some cooling load. Maybe we can deal with the lighting efficiency some. There's a lot we can do with the envelope, which is in the green. So let's just move from here. So the next thing, and by the way, so in this simulation, not saying you're going to be doing it, but we have these zones defined, right? And so we can edit any zone and set different, we can change different variables in terms of the loading, the HVAC system, the building envelope, and these settings are just the what we're assuming in terms of carbon footprint and energy cost. So we have these variables that we can set for each zone. We can also, and we can define in any zone that has windows in it. Those have already been, they're automatically added in the model, and so we can change um, the variables or the performance of the windows, etc. So let's just do that. So what I did first is I optimized, or I set the envelope at energy code standards, basically. So this is ASHRAE 90.1, which is the basis for the International Energy Conservation Code. Um, and that just meant coming in and adjusting my envelope. And so I have all these, not you see 90.1 2019, that's just saying this is an envelope that's designed to the standard. But the point is here that then by improving the envelope, I went from an EUI of 115 to an EUI of 80. So that's quite good. And if we go back and look at it, we'll see that a lot was changed in the envelope, which makes sense, right? So this is the way to use this tool. It's an iterative total heat loss or total energy efficiency um, simulation. So the point is that that's what, at least in my sections, I focused on last semester because that's what we would use to design the building. Then once we get to needing to understand the HVAC system, that's when we need the peak heat loading because we need to understand the most heating or cooling we're going to need at any moment because that's going to determine the size of the HVAC system. That makes sense, right? The more water or air of a certain temperature we have to move, the larger, or that changes the system that we're going to design. And especially, for example, ducts, the more heat or cool we have to move, the larger the ducts need to be. It's pretty simple. Okay, so let's just go through these quickly. So I have now, I optimized the envelope or I changed the envelope and went from 115 EUI to 80. Then I went and I adjusted the lighting density. Now, why I did it in this order? Actually, this wasn't, well, maybe it's confusing. Maybe I should have done glazing next. Doesn't matter. I just want to explain what I did. Then I went in and I changed the lighting density. In other words, I made the lights more efficient and I set dimmers, so automatic dimmers, and that decreased our EOI quite a bit to 68. Then I went in and changed infiltration um, to zero point 0.1 CFM per square foot at 75 pascals, which is very good, but it's not the best. So like Passive House would be 0.08. I've seen 0.06 set, and I think even in their sample model it was like 0.4. Anyway, so this is pretty good for infiltration, and look what happened, a drastic change. So from 68 to 35. What does this tell us? Well, first of all, that our envelope is less important than our air tightness in a building like this. Why would that be true? It's because air volume is having a larger effect than surface area of our walls because this is a really large building. If you don't get that, don't worry about it. It's just, I'm going through and showing you that how we're optimizing this envelope before we then look at peak heat loads. Next, I went and changed my glazing. So I used a really, this is triple pane, really low U value, but a high solar heat gain coefficient. So we're getting the benefit of solar heat gains when we need them. And that did a pretty good amount from 35 to 26. So our glazing helped a lot. Then I added some exterior shading. I didn't spend a lot. I just did this. There's a setting in the model that you can set. It didn't change it much. I should probably go actually set some real shading and see what I could do, but I'm not. I'm already at 73% less than the baseline. Then I added an ERV and then with an economizer cycle. Let me explain that really briefly. So right now, before I add the ERV, I was ventilating, so because I need fresh air, but I was just pulling in fresh air from outside and dumping exhaust air to the outside, and that means I spent all this effort getting a specific indoor temperature and relative humidity for my air, and now I'm just wasting that by dumping it outside because I need fresh air. So what an ERV does, or an HRV, an energy recovery ventilator, um, It allows us to exchange the heat and, in an ERV's case, some relative humidity with our indoor air as we're dumping it outside to get fresh air coming in. So we can then save a lot of energy that way because we're getting fresh air, but we're not losing energy. An economizer cycle is simply a setting that says we're going to turn off the heating and cooling coils or whatever it is that we're using when the outdoor temperature is in the correct zone, so we can just bring in fresh air without having to heat or cool it. So anyway, that from where we were before, a pretty large jump to 20. Oops. I'm really noticing, by the way, this is just that now hit me. It's always so much slower when I'm doing these videos. It's because the video's on and it's taking up bandwidth on my computer. So sometimes like double, triple clicking. I got to wait. I got to be confident. I got to be patient. Okay, anyway, so then the final thing I did was I looked at the HVAC equipment settings and I increased their efficiency. So I set the coefficient of performance of the heat pump higher, and I made the boiler a little bit better. And that also did a fair amount, right? And if we'd have been looking this whole time, we could see how these. So now we can see that mostly we're at mechanical ventilation and infiltration are the so in other words, this is heat we're losing through that ERV still, and this is heat we're losing through, or heat one direction or the other through air leakage. Anyway, we're doing great. We got 81%. The reason why seems so large, it's not that large. It's just because these are all so small. But if we go back, we at some point that made that drastic change because we improved the other things enough so that the mechanical ventilation and infiltration became the most important. Only point here is that now I've got an optimized envelope, and we're going to use that a little later. I'm going to show you a plugin in Grasshopper that they're developing for this that would allow us to size the HVAC and actually compare different versions. Anyway, but let's not go there. I'm not go there yet. So what we did is we just optimized this building for its envelope and somewhat the HVAC system. All right, so now let's go to this guy. Remember, we're heading toward a completed model, but I'm going to go through every single input on this uh, um, spreadsheet or in this calculator to explain what it is and why it's there. Um, and then you can ask me questions in class, please. We'll go over this. And if anybody in another section wants to ask me questions, you're welcome to email me. Okay, a few things about this. These are all set up with. All the calculations are. The equations are preset in the cells. By the way, this number division divided by zero, this means it's when I have nothing in here, I'm dividing by zero, so I get an error message. I can actually code this to where I wouldn't see that. It would just make these equations more confusing, and so I decided not to do that. Let me talk to you a minute about equations in Excel and how I set these up. You see that, so I've got some variables over here. And where it says name, these are actual names of these constants. So this cell is named CD, you see? And what that allows me to do then is wherever I use this number, that's going to be something that I use throughout a design, then it will show up. Like for example, here's TC. If I click on, if I'm in a cell that has an equation and I click on it, it's going to show me what cells are in the equation. In this case, one of them was TC right here, right? So I try to make my equations have constants that are named so that if you're clicking on if you're looking at them in this formula bar, you have some idea what they mean. The best equations are where everything is named. You can't always do that. Anyway, so that's a basic idea here. Another thing about this spreadsheet is that this color key here is something you should pay attention to. Blue means a variable. That's something that you can change at your heart's content. An orange cell is the result of a calculation, so it's going to automatically update. You should not mess with those. If you go in and type something in an orange cell, you're going to screw up the equation that's in there. I could have gone and locked these. I haven't done it. I have Of course, a copy of this that you can't mess up. Constants are things you could change, but I'm saying maybe don't change them. They're numbers that I set for a reason. The green is a drop-down list that just shows you that you can drop down and pick a number. And if it's gray and has an NA, it's just saying that there is no value that's related to that variable. Okay, so let's input this building. So first we have climate. What do we have? What's going on over here? Um, if you look at our assignment, there's a definition of cooling design temperature and heating design temperature. That's essentially, it's very simple, and but if you look at it in engineering textbooks or spreadsheets or whatever, it looks more complicated because there's always a percentage associated with it. And it's just simply you're saying, okay, out of all the hours in the year, how many are above this temperature or below this temperature based on heating or cooling? And if you have a design temperature, a 0.04% design temperature, that means whatever number you type in there for your climate, there's only 0.04% of the time that temperature it's above or below that temperature, based on if you picked a cooling or heating design temperature. So we're not even doing that right now. We're just picking a number and saying we're only designing our system up to this temperature. And so it might be that, let's say there was, so in our assignment, we said 95 degrees for cooling. Now we know it gets above 95 degrees sometimes in our climate, but I mean, how many hours a year? And we're saying in this design, we're saying, okay, you're going to just open the windows, or you're going to go outside or something, or you're going to have, we'll have we'll have a little, a smaller little personal air conditioner you can use, whatever. So there's the idea being we're not going to design a whole system for every single hour because that would be inefficient. So we've got a cooling design temperature. We're setting at 95. Our cooling set point, let's set it at 72. That's a fairly normal set point. And we're going to set our heating set point at 65. Why would those be different? Because in the summer, you're going to be wearing less clothes. It can be warmer and you'll still be comfortable. And then our heating design temperature is 15, we said. And so you see what happened is that then these two values generated this delta T, right? So my TC is the change in temperature between the cooling design temperature and the cooling set point. The same thing for heating. And it's good for you to play around with these. Like, let's say we put in 100, this should go up. It did, right? So just play around with this, if you're into this, play around with this calculator and it'll help teach you things. Okay, so that's the first thing. In our climate, and actually I'm just going to go ahead and put in for a we're going to set these. We're going to say that we have these climate-driven variables. We also need, and this isn't something we have done yet really in this context, but I'll hopefully be able to explain this as we go. We need to know what the peak solar gain in the cooling season is. Why would that be true? What we're trying to do is find the worst case scenario for heating and cooling. So when the sun is hitting a window in the winter, that would be an advantage sometimes because we want to gain that heat. However, it's never going to be at the peak loading time because the peak loading time is going to be at night when the sun is down. So we really can't take advantage for peak heating loads. We can't take advantage of the sun. However, the peak cooling loads may be affected by sun because the sun is going to be out at a time of the day and the year when we have a peak cooling load. So we would actually have to add this to our cooling load. So how did I get these numbers? I opened up Climate Studio, or Rhino. I made a simple model. I made a simple model in using our climate. So I did LaGuardia. I just made a box, and then I ran a radiation map simulation, which we did last semester. And So all I did was just I set this ground as concrete, and this all these walls were also concrete, and I was able to measure the peak solar gain on any of these faces. And so how did I do that? First, if we came in here, you can have all hours, but I don't want all hours. I want just when it's warm because I want the cooling load. And I want, so then I can see here, all right, I have my maximum month is July. And so I can go and select a sensor on any of the walls, and I can get an average. Or I can come down here and I can just, so this is kilobtu's per day per square foot. Oh no, it's the number of square feet. So if I take this, and this is kilobtu, so just if you phase out here, that's fine. I said, okay, 440 divided by 2.153 is going to get me kilobtu's per square foot per day, and then I divided that by 24 to get per hour, and then I came up with a number that I put into my spreadsheet. And so that was this, the 8.5 for, and then I did that for all of these faces. That's how I got those numbers. They should be somewhat accurate. So I picked the peak time that there's sun hitting the peak month, and then I calculated an hourly peak. All right. What else do we have? We have some constants here. Let's go through these one at a time. This 1.08 BTU minutes per CF for cubic foot hours degree Fahrenheit. This is a constant we use in, actually let me go to, oh, I don't have that on this one. Let me go look at this version. I'll put this in your template also. These are the equations I used in this calculation, or this calculator. Um, and we were just talking about the air constant. So when we're talking about infiltration or ventilation, we have to so we have a leakage rate. We have per area. We have a temperature differential, and then all of that we need to convert to BTUs per hour, and we do that with a constant that basically says this is how much heat air is going to move or is going to contain at this temperature. So when we're losing that air through the envelope, we need to know how much air. So we get that by the leakage rate, the square footage of the exterior surface of the envelope or whatever we're measuring, a change in temperature, and then how much energy is carried in that air. All right, maybe that's a little confusing, but I mean, well, I'm going to stop saying that. Just explaining that's why that's here. That's being used, and we're calling it air in the calculations. It's something we have to use in our uh, in the equations in the spreadsheet. Then these I set. Um, these are all from ANSI 62.1, which is standard for ventilation, and they're just the fresh air per person in the different zones you might use. Then the leakage rate is back to we just talked about leakage rate here. This is CFM at a certain pressure per square foot of envelope, and we're going to use that in equations also. Then we also need to know how much the internal heat gain per person is, and that's going to be in BTUs per hour. Then I have some terms down here that you should already know probably, but I've just defined them with their units so that you can come refer to them. Heat transmission, we're calling that U value. Resistance to heat transmission is R value, which is 1 over U. Peak heat loss is Q. Envelope exterior surface area, I'm just calling area. Solar heat gain coefficient, SHGC. And total solar radiation at the peak cooling, which is these numbers up here, is sol cool. Anyway, etc. So let's see how this all. So those are the terms that we're going to use. You can come and look if you're looking at a row up here. You don't get it. You can refer to this term section. Okay. So let's start filling in this uh, calculator. So this building, I'm going to go back to the architectural model. This building is 150 feet on the long side, 100 feet on the shorter side, and the long side's north and south, or actually east and west, but the face of this is north and the face of this is south. And then it's about 36 feet tall. And so if I take those, and I'm calling, let's see, let me go back to the zones. I'm calling the south zone 1, north zone 2, east and west zone 2 and 3, and this big central zone, zone 5. So then I can come in and fill in all the values. So for the roof, it's going to be 100 by 150, right? So the floor and the roof are going to be the same for these. So it's 1550 and 1550. And again, that's just simply taking the square footage of each of these zones for roof, floor, um, and then the walls. Oh, and by the way, I should say this too. I did not. I'm only doing one floor of the building. Okay, so I'm acting like we're at the bottom floor. I'm just using a model that already existed. So we're really just doing this floor. So there is a floor for each. There wouldn't really be a roof because there's an adiabatic floor above it, something it's not going to lose heat to. But I'm going to pretend like it's one story, so there's a roof on it. And then the walls for this are 3240. The R value, I can determine myself. I can design it, or I can look up in this chart um, on the chart page, on the lookup page. Let's see. If I'm going to have insulation, we're in climate zone 4. I'm going to say my roof is insulation is completely above the deck, so it's going to be R33, and CI means continuous insulation. All right. So I'm going to come back here and put in 33 for the roof. And you see now this has populated my heating and cooling load because I have all the variables I need now to define that. Um, and again, remember that it's a pretty simple equation. The peak heat loss, right now we're using R values, so this would be 1 over R instead of U here, but it's going to be just the U value times the area times either the delta T for cooling or the delta T for heating. And that's where these numbers are coming from. I'm going to go, let's see, I think for the walls, I'm going to make the walls, I'm going to make the walls R20 and the floors R20. Now, whatever, I can come back in and change that later. It's not really, the point is we're designing that, so we can do whatever we want there. This is actually the same for for zone 2, right? Because it's the north and south are the same. I mean, I could change them. I could design them differently, but I'm going to go and just repeat that here. But let's keep going down. So now I need to figure out my glazing. One thing I did not say is that, so these areas are for the opaque. I'm sorry, I should have said this. Opaque meaning anything that's not glazing. And so I could have made this more complicated, made it where you could have typed in, the length times the width and then the percentage of opaque. I just decided you should just calculate that yourself. So this is based on 60% opacity. So these numbers are 60%. The areas for the windows are based on 40%. So 40% of the entire zone is 2160. The U value, let's go look up something here. And again, these are minimums. So, well, This would be the maximum U value because the higher the U value, the worse it is. For the R values, these are the minimums. But anyway, so let's put in, I'm going to say, let's just give it a point 3. And, okay, point 3. Now I've got I'm saying this is the south facing. So south is 8.5 I see over here. So I'm going to choose my 8.5 like I did. I'm going to give this let's just put in this is above the code, but I'm going to go ahead and put in point 0.7. One thing I didn't mention here, shading, glazing shading. This is just simply a percentage of how much you think you're going to shade. You want to shade that wall. I'm just going to put 0 in for right now. But if I changed it to 10, it's going to adjust that number, right? Now remember, we've only got a cooling load here because we're saying that the solar aspect of our solar heat gain is only going to affect cooling, so we're not at the peak cooling load. So we're not going to worry about heating. It won't affect it. Then we need to come up with our internal heat gains. So how many people? Let's say this is I don't know. I'm just going to put in 5 because it's an off. Put in 10. Whatever. This is going to be something you're going to determine yourself. I'll go back to 5. And this is then calculating, it's just the number of people, the heat gains per person, we get the total heat gain. Infiltration, the area here is simply adding up the walls, roof, and windows. I didn't do floors because I'm saying there's no infiltration through the floor, which isn't really true. I mean, because this floor is probably on grade. I should say that also. I just decided to skip the whole thing about the perimeter insulation. I just said we're going to call this a raised floor even if it's on slab. You can ask me about that in class. So if you remembered that from last semester, what was that perimeter insulation thing with that constant or that variable F? We're not worrying about that. This is a basic model. So we need the area that the air is going to leak through, the leakage rate, which I'm going to put this is really low. Let's put this at 0.1. No, actually, I should have changed it over here. Oops. See, I think I just screwed up there. Yeah, see what I did? That's bad. I'm thinking I'm going to have to go. I put in a number and it actually got rid of that equation. So I should probably go protect these cells. But anyway, I'm going to change this over here to 0.1. So then we have an area of the envelope that's the leak's going to go through, an amount of leakage per square foot. So the square foot times the leakage per square foot is going to give us the leak. And then we have the air constant thing over here and the additionally in that equation. And anyway, so now we have a peak heat loss for cooling and heating based on infiltration. The final thing we have to do is ventilation. How does this work? We're just simply saying, okay, we have how many CFM per people? We're going to say this is an office or lobby, so we're going to call it 5. And that's all we need because it's just the rest of the constants are in this equation. I mean, we've already defined them. Peak heat loss to infiltration. And again, all these equations, I'm just showing you where they are. If you're somebody who likes to sort of dig into this stuff, which is what I do because if I can't understand it if I don't go in and try to figure out the units. It all does really make sense once you spend the time on it and just go look at all the units and see how they cancel out. Anyway, this is what we're doing right now, and we're saying area times leakage times no, I'm sorry, the ventilation right here. It's people times the amount of air per person. Skip this for a second. Times that air constant times delta T. This is simply the efficiency of the ERV. So if I have a 95% efficient ERV, then that's going to be a very small. It's going to multiply times this CFM and make it much smaller, right? So we're not going to lose very much heat. So that's what happened here. If I make this 0, I've got 1200 and 2,500 BTUs per hour in heating and cooling load. But if I make it 95%, which is totally doable, I can really drop that down. Okay, so now we have a we have something. Oh, because I'm in the wrong thing right now. Sorry, I didn't. Let me come back over here. So I'm going to make this 95, and so now we have. And let me just get rid of one. Well, because we did this, I probably shouldn't have done that yet, because I want to make this as clear as I can. Okay, so now all we have is the zone one completed, right? We have, and this is just the sum of all the cooling loads, the peak cooling loads. This is the sum, and then, okay, so what's next? Um, we've got a cooling load and a heating load. Now we need to figure out how many CFM we require for each of those, and then pick the one that's largest to define our ducts, to design our ducts with. Hopefully that makes sense. So we're just, and this is, by the way, everything we're doing is just when you went to the book and looked up, rule of thumb, tons of cooling. That was just a simplification of all this stuff. We're just kind of dialing in to get more detail and allow us to adjust things in a more nuanced way if we want to. So the thing I need to actually, this has a number in it just because of the way the calculation works, but I need a supply temperature. And why do I need that? It's because if I come over here, um, now we're using this equation. We're saying the air volume for duct sizing, so that's going to be in CFM, cubic feet per minute, is going to be the heat loss divided by that air leakage constant, or that how much heat is in air constant, times our set point that we're that we're bringing the air into, so 72 or 65, depending on the heating or cooling, and the supply temperature of the air we're bringing in there, right? Because if if you have a boiler, you're probably going to be delivering 110 degree supply temperature. If you have a mini split heat pump and you're cooling, it's probably going to be 55 degrees. So the difference between 110 and 65 is big, and the difference between 75 and 55 is smaller. So that's going to have a big effect on how much air we need to move. You just have to look at that and think about it, or we can talk about it in class. The point is then, so I need to have a cooling supply temperature. So I'm just going to say, and this is something we'll just talk about makeup, but typically for for cooling, 55 is very common. And I'm going to say this may be I'm going to say 100 degrees um, for heating. It might be less if this was all a heat pump, and we can talk about that. Um, the point is now you see that um, we have a larger cooling load, but smaller CFM. Larger heating load, smaller CFM, right? Um, what I'm trying to say is that the heating load is larger than the cooling load, but the amount of air we need to move is less because our set point is different, our supply temperature is different. And if you don't get some of these things, you can just fill in the chart and get outputs and then try to figure out what's going on. Okay, so then from there, if we were just talking about this one zone, we would keep going. We'd say, okay, now I know that I'm going to, in this case, my heating load is going to drive my duct sizing. And so how big a duct do I need? I'm now going to use that um, online calculator that Professor Thomas found, which I think is awesome. Um, and by the way, there's a little demonstration video right here to watch, which is very helpful. I'm just going to leave this on metal ducts, US units. What was our CFM? It was 23. No, I'm sorry. We're doing cooling because this is larger, so we need, let's say, 3,000. So I'm going to have a 3000 CFM. In the video sheet, just uses zero point 0.1 as a default for friction loss. You need to have something that's determining, you need a variable from this drop down. Let's just use friction loss. The duct height here is just so if we want to limit our duct height, then that will adjust our calculation. But we already see now that we have then, so this is, if it's a rectangular duct, we have 18.23 times 18.23, I mean 18 by 18. And this is our then cross-sectional um, area, our profile like we were talking about last week. So if I say, I'm just going to go 18 times 18 because we don't have to be that exact. We've got 324 square inches now. So I'm going to put 324 in here. Actually, we were doing feet. I kept changing my mind if it should be feet or not. So 18 inches is 1.5 feet times 1.5 feet, 2.25 feet. And then why did this branch go to 4? The branches are always larger because they have more. There's more surface area because they're small. I mean, the total branch uh, square footage is always larger because, and I'll just draw this in class if somebody asks me. But if we have a really large trunk duct we need to carry the same amount of air in the branch ducts, but they're going to be smaller. So that means they're going to have more surface area per duct, which means they're going to have more friction. So this is just a rule of thumb. I just used I went times 1.7. Because I just based that on what the changes that were happening between trunk and branches in the book chart. That's all I did. Um, and now if we go, so now we're essentially done, except for now I would also need to go look at my trunk for my fresh air. I mean, my duct sizing for my fresh air. This is going to be tiny, and I didn't mention this, but now we also have a fresh air um, for our fresh air ventilation. I think we should have a completely separate ventilation system. Well, maybe not. I'm just saying this is the amount of fresh air we need in addition to the air we need to move heating and cooling. And we're just getting that from um, CFM per person and the number of people in the zone. So we've already got those set. And you can see it's a really, if we only have 5 people in this zone and it's not a gym, that's going to be a small amount of CFM. It's not going to make that much of a difference. Um, but if we come back to our trunk, so let's go and let's just up it. So no, let's not. We'll just see how tiny it is. Where are you? So what did we say? We said 25 CFM. Oops, not 52, 25. Yeah, we've got a 3 by 3 inch duct. So I'm not even gonna 3 by so um, so 3 times 3 divided by 144. All right, that's 0.06 square feet. So I'm going to leave that off right now. That's why I went back and forth between the square footage. So maybe I should probably just go back and change this to where this is. Oh, I did. Look at me. Look how smart I am. Oh no, I just screwed up because this is square feet now too. The point is, I guess it doesn't really matter. This is just whatever you want it to be because it's just simply you're typing in a number you get from the duct if you're using that same duct calculator online, and then this updates it with times 1.7. So we could use square inches here. Let's just do that. So what was it? It was 3 times 3, so that's 9 square inches. All right. Now all we have to do is do this for all the zones, right? And so I already said that, well, actually, I'll just, so I could come in and I know that this is going to be the same. By the way, it's if you select cells and hit Control C and then go to where you want to place them, hit Control V, it'll update. So I could go through and do this for all my cells, or I can just come in here and show you the final version that I did before, which is here. I didn't do all the trunk ducts. This is square feet. No, actually, this is square inches still. So whatever. I'll fix these little mistakes I'm finding. But so now in this case, we have a complete a full cooling load and heating load, so we can look up equipment, or we can just say this is the sizing. I would suggest starting to try to look up equipment, and we have separate CFM uh, requirements for each zone that we can then come and determine our trunk and branch sizes for them. If we're using ducting, if you're not using ducting, you don't have to do that. That's another thing we can talk about. I can't imagine not using ducting in the gym project. So if you come up with a way, great, but I'm not sure what it would be right now. Um, so the last thing I want to say then is, what do we do with this? Okay, you can just write down 15 tons and 200 BTUs per hour, 220, or we can look up some equipment. So like I just looked around, um, and just type in descriptions. Um, here's a single package VAV unit. Um, it's plenty. It's huge, I think, for our needs. Well, it's 12 to 24 tons, so that's what we need. Why isn't it saying anything about heating here? Well, it's because it's not really for heating. You can have an optional electric heater, which would, I think that means strip heating. I don't not, or that might mean I don't know exactly what that means. So we could look in the specs. Um, so with this one, you're probably going to use a boiler, I would imagine. And some people had that option in on their assignments last week. Um, but this is actually a pretty small project, and so if we had, here's another one that I found, and again, this took 30 seconds, so I'm not saying these are great. This is a rooftop, a roof-mounted heat pump unit that has 3 to 5 tons of cooling, so 36 to 60 thousand BTUs of cooling and 36 to 57,000 of heating. If we come back and look at our, so for each of these zones, this is, so it's 12,000 per, 12,000 BTUs per ton. So this would be 4 tons, 4 tons, 3 tons, 3 tons, 3 tons. Those would also, we could use a separate rooftop unit for each of these zones, and that would work for this unit that I found. It'd be very small, very simple. Um, and now we're over here in the heating. That's good. That's maybe pushing it a little bit, but I think for our purposes we could, because it's saying that we're, um, you know, that we're what? Yeah, we're at 57. Maybe we'd find a larger one then, or we would come over here and say, is there a way that I can change, tweak this so that I don't have these larger loads in those two zones. All right, so that was long. Let's see, how long was that? um, 53 minutes. Uh, I realize that's a lot, and we're not mechanical engineers. Honestly, though, what I did is I said, okay, I'm going to go through and think this through at the level we need to understand it in this class and make a calculator that will be as simple or modeler as I can make it and try to explain it. So that's what I've done. Um, Hopefully it helps, and we can keep working on this. Talk to you soon.